Okay, welcome everybody to today's California Dreams Technical Seminar Series talk. We are lucky every week, and I probably say something similar every week, but it's true. We are extra lucky this week to have Rehan Kapadia as our speaker. Rehan is associate professor at USC. I hope I got that right. In the Ming Department of Electrical and Computer Engineering, where he joined in 2014. He holds the Colleen and Roberto Padovani Early Career Chair here at USC. Graduated from University of California, Berkeley with his Ph.D. in 2013. Has won a number of awards, including AFOSR and ONR Young Investigator Awards. Peter Mark Memorial Award from the ABS, and has interests at the intersection of material science and electrical engineering, focusing on non-equilibrium electron devices and materials growth technologies for next generation electronic and photonic devices. But more importantly for us, he is the incoming director of MOSIS 2.0. We are very grateful to Mike Haney for his service as the founding director of MOSIS 2.0. And Mike will continue to work with us, but Rehan is taking over the position of director of MOSIS 2.0. And we're very excited to have his new ideas coming in. And rather than give a longer introduction, I will let him tell you about the way we're going with MOSIS 2.0 and the direction he's taking us.
Yeah, thanks so much, Steve, and thanks to Jay for inviting me for this. I will also be giving a different seminar on research July 11th. So if you don't like how I'm doing it today, you shouldn't show up to that one either. But what I'm going to talk about today is MOSIS 2.0, and I'm going to kind of go through what we're doing with MOSIS 2.0 and kind of where we see ourselves going. So to give some background, I have been working in the material science and devices field for a very long time, focusing on growing new materials, integrating new materials, turning them into both electronic and photonic devices, and then looking at circuit applications or system applications of those new materials and devices. So traditionally I would be characterized as a device guy. In fact, when I posted about this on LinkedIn, one of my colleagues who did a Ph.D. with me at Berkeley at the same time, so we were there from 08 to 13 doing our PhDs, and he said, "Oh, I have got my first two. I did my first two tape outs through MOSIS," and I thought that was a little bit funny because back then I think it would have been very unexpected if out of the two of us, I were the one who ended up becoming the co-director and then director of MOSIS 2.0. But here we are. And so what I wanted to do was, through this. Give me a second. I hope everyone sees my slide change. So through this talk, first I wanted to actually talk about a little bit about the history of MOSIS, and when I say history of MOSIS, I really mean looking at how MOSIS did things when it first started. I know that there's a lot of people here, a lot of people know what MOSIS did and how it did it, especially in the later years, maybe in the last 20 years or so. But I think there's something really inspirational about what they were doing in the first couple years of MOSIS, and I think it also provides a nice template for us to think about how you accelerate research innovation. You accelerate research and innovation. So talk about that, then maybe try to extract some lessons. So this will be my own opinions. The history will in fact be facts. Then talk about, briefly mention something about the challenges of accelerating research and transitioning research. And then we'll talk about what we're doing today. And we'll cover both what we're doing today as well as our operating model, our services, and then kind of where we see things going. So, with that, I wanted to jump in. So this is a slide that I actually stole from Steve. So I think Steve gave a presentation and started with this. And, the thing is that Moses, the original Moses, was not the first ever aggregation multi-project chip or multi-project wafer. So the first was basically carried out by, Lin and Conway in order to teach a VLSI class. And the reason that they did that, if you go back and you read, it's that before that, before this aggregation and essentially aggregation of chips and disaggregation of design and process, in order to really be able to design circuits and get them fabricated, you had to know both something about design as well as something about fabrication. While in the 1970s, fabrication, compared to what we do today, could be considered trivial, right? At that time, it was, a very large lift to be able to understand the minutia of the details of actually fabricating devices as well as designing circuits. And so the concept there was, okay, well, if we can put a layer which abstracts out and takes care of the details that designers don't need to know in order to be successful, then what we can do is we can train an entire generation of, and obviously more than one generation now, of circuit designers where their major focus is on circuits and they don't need to spend a whole bunch of time learning details about fabrication that frankly doesn't help them design circuits that much better. And also, obviously, then immediately what it does is it massively opens the aperture to who can use these or who can contribute in that area. So I think that, in terms of the textbook, everybody knows about it. And I think many people also understand that they were the first people who did this. And, at the same time, DARPA was thinking about, how they actually build hardware for all of these different pretty radical ideas that they had. And so that's, coming together, these two things coming together, that's where, Moses, the original service, was founded. And so, the concept was, okay, well, at ISI, we have ARPANET, we have a lot of fantastic people. And so Danny Cohen was basically tapped to lead the first, be the first director of MOSIS. And, he was I think an extraordinarily distinguished person who has contributed across many, many, many things that we all know about. But I think that the key point to generating MOSIS was that now DARPA researchers, at the beginning it was just DARPA researchers or ARPA researchers, had access to be able to rapidly and cheaply test their ideas in hardware. And so that's what, led to the founding of MOSIS, and that was the real mission at that time, and that was why it was funded for so long by the government. So what I wanted to do is take a few slides and just kind of talk about, well, what was MOSIS in 1981, right? What was the workflow? How did people actually do things? And the reason I want to go through this is because I think it's very impressive what they were doing in 1981, which was multiple years before I was born, and how automated that process was. So basically, what people would do is people would use email because ISI was one of the nodes of ARPANET. So they would use email and FTP to send their designs as well as talk to Moses. Moses would take people's designs and in an automated way they would do checks. In an automated way they would do layouts, and in an automated way they would do aggregation of the designs, which is very, very impressive for something that was done in the early 1980s, but is also something that is really critical and was critical, I think, to the success of MOSIS. And then on top of that, in order to really enable this separation of the designers needing to understand what's going on in the fab and just let them design. They added in a bunch of process control monitors, and they would basically serve as the people who understood yields and understood the challenges associated with turning designs into hardware, and how to make sure that the designs that your designs, you would able to at least be able to get a single working design back. So that was actually a really important part of it. They would also get it fabricated. They would do the testing. They would do the packaging, and they would send it out. And something interesting is that there was a couple of options for packaging, so it wasn't like you had just one option, but it was maybe only like 3 or 4 options to do the packaging back then. And they had a really interesting automated system to respond to emails through something called MOSIS control language. And this is from a 1984 report, ISI report. So this is not a real language, but I mean, this is not real communication with the customer. But essentially, someone could send an email, and if you send an email and it wasn't using the proper Moses control language, it would say something like, it would basically give you instructions. Say, all right, well, you sent something we don't understand what you're saying. Here are your options. And so you could send, you could then basically say, all right, using Moses control language, you could send these requests. Okay, I have an information request on topics. I have I want the user manual. I want to know about the schedule and the technologies. This is a incredible feat and an incredibly forward-looking thing to do in the early 80s. Of course, people could also mail stuff if they didn't have access to email at the time. So you could physically mail things as well. And then you could also send your files. You could check on whether there was automated checking. So you send your file in. You could check if it met the necessary criteria. And if it did, everything was fine, and it would say if this is good. If it wasn't fine, they would respond, and they would say no, you have to resend it. And then you could even go through and you could check on the status of what was happening in an automated way. So just incredibly forward-looking, and really took advantage of what was occurring in the technology space around them to reduce the amount of manual labor needed, which is, of course, a theme that I think since the 70s and the 80s has been, continuously applied to every field possible. They also did, automatic, like I said, automatic project aggregation. So they had these. These are actually figures from a 1997 paper from Ronald Ayers, who wrote, I think, a lot of Moses software over the years, and basically showing how they did what the algorithms they used for automatic layout and aggregation, the algorithms that they did to then convert the files into these MIBIS files, which is what they needed back then, and then also automatically doing bonding wiring diagrams. So essentially, there were certain chips with certain bond pads and then certain packages, and then automatically doing the kind of the wiring so that there were no crossing or overlapping wires, and everything was as short as it could be. So very, very forward-looking and very, very inspirational to really look at that and think about what they were doing back then. And there were many early successes, but I would say that the biggest success was that from the history books, it's the cost of doing full foundry runs were likely on the order of about 100,000, maybe a little bit less, of course, with some variation. But then what you could do with Moses was you could get something taped out for a few $100, so maybe $500, $1,000. And then you had options to design your parts with standardized pad frames that they might have offered. They also had early on, they had a repository of circuits that you could designs and circuits that you could get access to, via this Moses control language. And then there's also some really exciting demonstrations that were created, which is, for example, the first RISC microprocessor from Berkeley, from Patterson's group. There were some of these early, I guess, precursors to the GPUs, which led to silicon graphics founding. There was also the Stanford MIPS CPU, which led to, MIPS. And, when I look over what was happening geopolitically at the time, there was really a major race between the US and Japan in terms of semiconductor dominance, so to speak. And what it seems like happened was that in Japan, there was a lot of focus on basically getting processes that were as as highly yielding as possible, and essentially trying to push the boundaries of process optimization. While in the US, partly because of MOSIS, people were able to have really, really risky designs and products tested out easily, and that led to real dominance in terms of the types of products as well as the companies that were able to establish themselves in the U.S. So while Sematech played a vitally important role in basically having the U.S. regain process leadership, I'd like to make an argument that MOSIS played a really important role in making sure that the U.S. maintained product and architectural leadership through those years. And so that really goes back to this idea that, well, if you have, I mean, the turnaround time then was 6 to 8 weeks, which I think any designer at this point, if people told you could have everything, a packaged part back in 6 to 8 weeks, you'd jump for joy. Obviously, designs were pretty simple back then, right? Anything that was done back then, we could easily redo in our nanofabs here today. With undergrads or even high school students. So obviously, that's not an apples to apples comparison, but nonetheless, this rapid time is really important for allowing the people who have ideas to be able to iterate and test things quickly and test things cheaply. And the faster you can test things and the more cheaply you can test things, obviously, the larger part of any research space that you will be able to explore. So that's a kind of a quick summary of the history as well as some of my thoughts about it. I think that and then I should say that there's been multiple eras of MOSIS. From the beginning it was purely funded by DARPA, then it was mostly funded by government, and then it finally became self-supporting, and then it was self-supported for a long time, and then eventually it basically kept offering the same services, and other people also started offering those services, and I think the relevance went down, because at that point you're not doing anything to accelerate researchers and startups' abilities to prototype and understand what's and understand the how good their hardware or their ideas are, and you're not doing it in a differentiated way. So in the end, that kind of went down. So then what happened was that now we have California Dreams and MOSIS 2.0. But before I kind of jump into that, I also want to talk about some things that I think are lessons from both the history of MOSIS as well as kind of our overall history in terms of building infrastructure, using infrastructure, and carrying out research in the semiconductor space. And I think that while this may be controversial to some, I think it's a very reasonable point to make, which is that infrastructure and capabilities of your infrastructure, which in here infrastructure includes tools and access to tools, it's the most critical part of enabling advancements in hardware. Because in the end, if you want to prove out something in hardware, you always have to build it. Otherwise, it's very hard to de-risk it purely from a software perspective. It's very, very hard to basically guarantee something will work purely using software. It doesn't mean that doesn't happen, right? I mean, there are stories about that, but in the end, for most things that are highly risky and innovative, you have to actually build a part and you have to test that built part before people believe that you have de-risked it enough to then put in the capital to take it to the next stage. And so that then brings it to the next idea, is that if you want to be able to test these highly risky ideas, you really do have to have somewhat cheap, and I put cheap in quotes because it varies depending on what area, what field, what application space. It varies what that means, but cheap and rapid access to this infrastructure is really important in order to be able to, enable people to explore their high risk, high reward ideas and essentially bring that level of risk down so that that next level of engineers and capital can go after it to mature it if it makes sense. And the other lesson that I think that we learned from original Moses as well as many other things is that standardization and automation are critical in driving costs down, right? What standardization does is it basically tells the designer that you can operate in a slightly smaller design space, and what that does is that constrains what you can do a little bit, but at the same time it takes many design decisions off of your plate, and it also allows you to get access to things that will work. So essentially, if you think of your hardware as a whole bunch of different subcomponents, you would then expect those standardized subcomponents to be a much lower risk part of the hardware. So now you've basically reduced the overall risk of your hardware working by designing into something that's standardized at the cost of some level of performance, which is probably true in almost any space. But in many cases, when you're just trying to demonstrate something, that trade-off is absolutely worth it, because you want to be able to do things quickly and cheaply. The other thing is that what Moses did by eliminating designers' need to know about the details of fabrication processes is that you reduce the knowledge barriers to being able to actually access something. And that is a lesson that we still see. And in fact, I've made the argument before that if you look at people who grow up in the circuit space and you look at people who grew up in the materials and device space, there is very little overlap in their training. And what I mean by that is you can't really take these people and switch them, because almost everything you learn is different in both of those areas. And so it just it's very effective in making sure that people can make progress in their given area, right? But then when you need to be doing things that require system level demonstrations and might actually require knowledge across both areas, it suddenly becomes very difficult. And so that's where being able to reduce these knowledge barriers one way or another. So in the 1980s, this was by kind of disaggregating the circuit design and the fabrication parts of the space. But today that might look like something different, given all of the things that are happening around us, and automation and AI and machine learning. And then the last part is that if you look at the life cycle of research infrastructure, right, which is very important. So I run a research lab which has many different pieces of equipment where we grow materials or fabricate things, and then we also have our nanofab at USC where we have lots of different equipment, and we try to bring in maybe 1 or 2 new pieces of equipment a year, but that also just naturally means we have a lot of equipment that is 10, 15, 20-ish years old. And so continuously updating that research infrastructure requires continuous infusions of cash. And that can become very expensive when you're thinking about how do you do something like this on a national scale. And so I think that when we look at our capabilities today, it also means that we have to think about how we can take infrastructure that was state of the art and was used to demonstrate very exciting things for the small group of experts that originally were pushing for it, and then see how we can, by lowering knowledge barriers and bringing in automation and autonomy, how we can then use those capabilities for broader sets of researchers, because then that essentially extends the lifetime of these very expensive capital purchases and research infrastructure that we install. And now that's a statement that's kind of, it's a general statement, and it's basically true across all research infrastructure, everywhere. But it is a real problem, and it is something that there are no good solutions to today. And I'm not saying that I'm going to propose a solution to this major problem that nobody has solved yet. I'm just highlighting. And so then to kind of go from our original Moses to California Dreams and Moses 2.0, this was started by a study that was carried out by Zach Lemnios and Brian Cohen. And so essentially they started to rethink, okay, well, what does it need to look like, and what is the Moses of the future, aka Moses of 2021, need to look like? And at the same time, there was the CHIPS Act that came about, and there was groups of faculty from USC, UCSD, UCLA who started to really think about what we can do, and then that expanded from just circuits to also include nanofabs and industry fabs, and that's kind of what ended up in what we now know as California Dreams, which is this hub. So I know that there's probably people who know everything about this, and there might be people who know nothing about this. So forgive me if I'm telling you something that is already known, but just to give kind of just to make it complete for those who aren't as familiar, California Dreams is one of the 8 microelectronics commons hubs. We're the Southern California hub, and we're focusing on electronic warfare and 5G, 6G technologies. And it's basically bringing together academic research fabs across the 7 large R1 universities in the Southern California area, which are the 5 UCs and then USC and Caltech. It's also bringing together our industrial partners, our industrial partners who have DoD or mid-scale volume fabs such as Northrop, Teledyne, and HRL. And we're also bringing together some system developers and system integrators across the major primes, so including Boeing, Northrop, Lockheed, and Raytheon. And the vision here is that we can now have unified access to not only commercial fab technologies, but mid-scale fab technologies, and the ability to prototype things at a single device or few device scale for very, very out there ideas that are too risky to be run in any kind of commercial, of course, but even low volume or mid volume fab. And so the idea here is that, well, with this umbrella of capabilities and talent, Moses 2 can essentially sit there in the middle and work to take potential customers' challenges and then translate them into solutions across this set of facilities. Now, what that does in terms of addressing these challenges that we talked about is, one, is it reduces the knowledge barrier that a customer needs to have. This wasn't a challenge I explicitly said, but it also reduces the administrative barriers that customers have, which is a really critical challenge. If you're trying to get anything done across multiple institutions, you just know how absolutely astoundingly difficult it can be. So by reducing both the knowledge and administrative barriers, we kind of look at ourselves as a single point of entry for people who need solutions that span more than what just a single institution either can or wants to do. And then by also working with companies such as PDF Solutions, which is a analytics company, is that we can start to bring in more and more of these. We can build up data sets for our research fabs and potentially our fabs as well, our DoD fabs as well. Obviously every data set is owned by whoever generates it. But we can then use those to accelerate our semiconductor prototyping projects, which means that you can speed up how fast somebody can go from an idea to an actual project. And you can also accelerate your lab to fab transfers, which is something that's important, through these analytics. And so that's kind of the overall vision there. Now, that vision is nice, but from a practical perspective, what it means is that we have at MOSIS a set of engineers, and these set of engineers have partner engineers at all of our partner facilities, and so that would include all of the facilities such as our research, our university research fabs, our industrial partner fabs, as well as the other technology providers who we're working. And by doing that, we have some people who kind of have an overview, but are technical, are real engineers, and have an overview of kind of all of the different capabilities, or at least a large set of the different capabilities. And then simultaneously, we have people in the facilities who are the experts at actually executing on those capabilities, those technical capabilities. And the ultimate goal here is to use this combination of engineering talent, data, and automation to be able to dramatically speed up how long it takes for a customer to come in with a request. And that request might be something simple like, oh, I want some kind of waveguide with something on it. So that's a relatively simple process that wouldn't take that many steps, maybe like 5 or 10 steps at most. To saying, all right, well, we actually want a small prototype wafer or system, and we want to be able to get it in instead of multiple years, we want to be able to get it all done within a year. And so essentially, this is the ultimate goal here, which is to be able to take all of this capability which exists and is generally used for its own specialized purposes, and by being able to combine it in a low administrative barrier and low knowledge barrier way, we can actually dramatically expand the set of customers that would be interested in accessing it and then can, in fact, access it. And so right now, the way that we've written our mission is that MOSIS 2.0 accelerates semiconductor hardware innovation through automation and reduces barriers to lab and fab access. We might change that in the future, but that's kind of a succinct way of what we kind of see ourselves as doing. And it is important to say that is really a mission, and the mission is to accelerate people's ability to test their ideas and test their ideas correctly. So I should say that while I've talked a lot about our hub, which is California Dreams, we also have close partnerships with MMEC, which is the Midwest Microelectronics Consortium, and ASU, which is the Southwest Advanced Prototyping Hub, so SWAP Hub, I should say, which is based in ASU. And so we are also expanding to be able to offer services that they have through MOSIS 2.0. And so I'll talk about that in a second. So I should say, well, all right, so what is MOSIS 2.0 and how is it really augmented compared to the original MOSIS? Well, what the original MOSIS did is it offered MPW access to commercial foundries. That's what it did, and it was pretty good at it. But that is not really the limiter in accelerating research and development anymore. There are a lot of services that give you access, MPW access to foundries. And so just doing that doesn't really serve the mission. Now, that said, there are also foundries that people would like to have access to, but don't because of various barriers. Those for example, some of these mid-scale volume fabs that are used for compound semiconductors and photonic integrated circuits. And so one of the first things that we've done and are doing is expanding to enable those fabs to basically give access to or run MPWs for customers. So we can run MPWs for customers for those fabs, and that's immediately increasing the access capabilities that people have, because for some of them, people didn't really have easy access before, and now we basically again can enable people to get access to them, but also we can serve as an interface, because unlike the commercial foundries, these are generally lower volume foundries, which means there's more work to be done in terms of educating the designers on how to use the technologies and how to design into the technologies, and working with the fabs to make sure that things come out the way that they should. And so that's something that we are doing, and I'll give an example of what we're doing there. One of the things that we're doing there. Another major change is that now we have these 7 pretty well-equipped semiconductor research fabs at our universities. We call them nanofabs in general, but I'm going to start calling them semiconductor research fabs, because I think not everybody understands what a nanofab is. But more people understand what it means if I say semiconductor research fab. And so what we are able to do and are already doing there is that customers can come in and say, we want this crazy idea tested out. And what a crazy idea means is that in general, if you're a company, it means, okay, well, this idea has been published a couple times, and maybe there's something interesting about it, and we want to be able to test it out to understand what's going on here and if it can actually work. And then we can actually work with them, build out process flows. We can then execute those process flows across multiple facilities without having to have the company deal with all of the administrative work, all of the financial work. We just act as a kind of a single point. We also basically develop the process flows, make sure that we help them do things in a way that will actually work based on the facilities. So very, very high touch, very much kind of going back to what the original MOSIS did, but actually at a step higher than that, because the process control that exists in semiconductor research fabs is lower than the process control that people used to use for production fabs, even in the 80s. Not because they can't do it, but because in general that's not the business. And then finally, we are also offering design services. So this is also an expansion of the business model, because that was not really part of what MOSIS did. And so the concept here is that we actually have a pretty deep pool of talent, design talent, as well as IP and reference designs that already exist inside, say, ISI, and we're taking those and we're basically making them available to customers. In addition, we are bringing on some of these early AI-based design tools to allow people to design into them. And so this is, there's some stuff that people have access to for digital, and then there's also some for analog. And then ideally, we are also expanding to IP that's generated through ME Commons projects. And so IP that's generated through the hub will be able to be served through Mosis 2.0, but not just served, meaning you get access to it, but also will actually have someone that helps you integrate it into your projects. And then there's also our goals are to expand this so that all of our partners essentially have the ability to put their reference designs and IP up and be able to clearly explain to people how mature it is, so that people can use it, at their, at whatever, with whatever level of engineering support they need. But essentially give people a way to take what they have done and make it, and instead of just leaving it in a computer somewhere, actually make it useful for other people as well. Now, to make things a little bit more specific, we have a number of commercial fabs and OSATs, as well as university fabs and low volume fabs. But I do want to highlight that one of the things that we're doing is we're expanding to a number of partners. So Sandia National Labs is offering their indium phosphide photonic integrated circuit technologies through us. ASU is / Swap Hub is going to be giving us, or we're going to be basically serving their packaging technology. And through Raytheon, we're also working with them to serve their their silicon interposer technology as well. So basically, we're expanding access to these places that don't necessarily have a well-developed front end for customers, and so we're basically using this to you know, we're going ahead and onboarding them and serving these technologies. So I should say that we have a number of capabilities, and so you know, essentially all of the capabilities on the bottom part of this table are new as part of Mosis 2.0. I will do a little bit of advertising that we are planning on having a Northrop Grumman GaN commercial MPW tape out coming, you know, in October, November timeframe. We also have a collaboration with MMEC and Northrop to run a GaN prototype accelerator program, which there will be more information about. There's more information about on our website, which there will be a QR code for later in this presentation. And so essentially what we're doing here is, you know, we are serving a lot of people on the traditional technologies that we have served people with before. And we are now expanding access to some of these new technologies. We've onboarded them, we have the capabilities, and we're running these various programs to actually make it easier for people who haven't potentially designed into these technologies before to actually start to design into them and expand that customer base for those technologies. And that, you know, that's important because it goes back to what I talked about earlier, in that infrastructure is expensive and infrastructure is capital heavy, and being able to expand the customer base for any installed infrastructure is almost always good. And to maybe take a small aside here, right? Why is it that our foundries, our commercial foundries, are able to do things in a way that's so much more yielding and well controlled than a mid-scale volume or a low volume foundry? Well, it's purely volume. The more that you can run a process, the lower your defect rate and the higher your yield can be, purely because you just get more tries at it and you can improve it. And this is something called learning curve theory that was developed by, I don't know, maybe Boston Consulting Group in the 80s. And that was done with some of the folks from Texas Instruments in the 80s. I might be wrong about that, but I think that's right. So that's called learning curve theory, and it basically tells you that in order to get the yield better for any manufacturing process, you have to be able to run more stuff. Now, that doesn't include what we're all trying to do today with data and AI and digital twins, but those are essentially just supposed to be proxies for running more stuff. That's basically what it comes out to, or getting more value out of a single run in terms of being able to improve the yield more per run. So that's the, you know, that's a little aside, but that's what we're also trying to do here, is trying to be able to actually give people access to various technologies as well as expand the set of people who can and want to design into these technologies. So I should say that since we're doing this and we're onboarding, we have a process now. So we've done this a couple times, and we're continuing to do this. So the first phase of bringing on a new technology is just we meet with the foundries and we say, all right, what are we going to offer, and choose one technology to offer, and then we kind of go through a process where our engineers sit with the foundry engineers and essentially learn that technology. Then we identify some set of customers, and that set of customers can come from within the hub, it can come from microelectronics comms, it can come from wherever. We run some kind of pipe cleaner MPW run. So we are doing one of those with Sandia National Labs, which I'll talk about. And then finally, we just have it as a storefront, as a regular offering on our storefront, where we have it priced out. We kind of understand the economics of what it costs us to serve that technology. We will have some understanding of, you know, how much support we need to give to various different types of customers, and you know, what it takes to be successful. And then it's just a standardized offer. And so this is an example where actually almost at the end of this pipe cleaner run for our Sandia National Labs Indium Phosphide Photonic Integrated Technology MPW program. And we're planning on offering this regularly at a regular cadence through Mosis 2.0 each year. And so essentially, it's pretty straightforward. You have your we kick off a program, we initiate the NDAs, we release the PDKs, we get the design submissions, we do reviews, we do the reviews, and we do the final verification, and then we kind of send it to the foundry for tape out, and then we get the parts back, and then there may be some packaging option depending on the technology and depending on what we're doing. So it's kind of a quick overview, but one of the things I will highlight is that our roadmap is a little bit more it's a little bit more ambitious than just giving people access to technologies, and a little bit more ambitious than just having IP repositories or reference design repositories and design services. Because while those things are quite valuable, I think another thing that we have to recognize is thoughtful customization and thoughtful standardization enables people to test their innovations in a system level by essentially allowing them to focus on their specific innovation and then get the rest of the system by designing into the system. So we're actively working on both prototyping boards that people can plug their silicon into. So prototyping boards with FPGAs on it, so that people can essentially outsource the blocks that they don't want to the FPGA and kind of focus on what they want to do as a rapid prototyping mechanism, as well as standardized interposers with different technologies, different IP blocks on them, which allow people to kind of connect their IP blocks and their chiplets to a standardized system, and then ultimately, having this kind of semi-customizable prototype systems where you have your silicon being able to connect to a board that has FPGAs, and then that has an FPGA, and that can then there you can integrate either an interposer, you can integrate your own silicon, you can integrate basically whatever you want on there, and that gives you this capability. So how am I doing on time here? I don't actually have a. Oops.
You've got about 10 minutes left.
Okay, so
or whatever time you want to allow for questions.
Much less time left than I thought. Let me do this. Okay, so now that's our commercial fab services roadmap, and I'll skip this. We also have lab technologies. So essentially, now, as I said, we're offering these multiple lab technologies through UCSB, USC, Caltech, UCLA, Irvine, Riverside, and San Diego. And so essentially the way that we're working with them is something similar to our fab technologies, where we kind of identify capabilities, we identify process maturity and tracking, we then put them on the storefront, and then we offer them, but then we also continuously iterate with the semiconductor research fabs to improve the quality of the offerings, not in terms of this breadth, but specifically in terms of the kind of the process control. And that's something that we're working on, and we have pilots going on with USC, UCSB, and UCSD. And the goal is to be able to transfer processes back and forth between these monitored facilities, as well as maintain processes from 1 year to the next in these facilities, while reducing the amount of engineering talent and expertise that's needed. And so I will skip on over some of these things. I do want to highlight that we have had some early wins on this, where we have done essentially tool matching across 2 different tools, one at UCSB and one at USC, on a single recipe. And then that has allowed us to transfer in one shot other recipes from one facility to another and almost exactly match the process conditions. So essentially we ran a bunch of indium phosphide etch processes on both the tools. we used our sensor data to kind of cross-calibrate, and then we were able to perfectly transfer a gallium arsenide etch from one facility to another. Now we're kind of expanding it and seeing what the limits of this process transfer and control are per set of calibration runs, which is super important for taking these facilities and driving them forward. And essentially, the goal here is ultimately that, you know, we go here, we build these process repositories, the fab analytics, you know, enable some level of autonomous process optimization, and then also bring in some device simulations for folks who want to design stuff. And then ultimately, this actually leads back to these customizable prototype systems where now people who can build and design and develop things in the nanofabs can also get some level of system level, it can get some amount of system level demonstrations through using these standardized, you know, but customizable, semi-customizable prototypes. We also do work for the ME Commons projects, but it's basically it's a mix and match of what we're doing for our fab and lab services, so I won't highlight that. And maybe with that, I'll go to these QR codes. The Mosis 2.0 one is, or the California Dreams one, are both allow you to see these the what's upcoming, especially in terms of these prototype accelerators and whatnot. So with that, happy to take any questions, and hope you all kind of enjoyed this blast from the past, and also then pathway to the future.
Thank you very much, Rehan. That was great. We have plenty of time for questions now. That was a quick wrap up to allow time for questions. I'm sure we have questions. I have one while we wait for other people to think of their questions. If you weren't born in 1981, how do you know how it was so amazing what they did in 1981? Maybe we were all doing that in 1981.
It's true. Maybe things were really amazing from 1981 to 1985, and then when I was born in 1986, everything went off the rails.
Yeah,
that's possible. I mean, you know, it's the sin of monotonically extrapolating that we all do. I think there's a question. Someone has
Priya, thank you.
You're welcome. Hi, I did really enjoy the walkthrough of what MOSIS was and what MOSIS is. My question is, suppose you have a project idea and you're not quite sure if it fits in the offerings or functional blocks you have at the moment offered through MOSIS 2.0. What would the process be to like kind of mix and match? You know.
Yeah, absolutely. I mean, I think you know, anything at this point, while ultimately I would love to have everything be fully automated, at this point, the best way, if you have something that is, you know, a crazy idea that needs, you know, really needs some thought, what we would do is we set up a meeting with our engineers and we kind of figure out, okay, is this idea possible to execute across the set of facilities that we have? And if the answer is yes, then we will try to work with you to do that. I mean, if the answer is no, the answer is no, we just don't have the capability. So that's what I would say, is that really comes down to what needs to be done, but you know, we have the engineering capability to kind of address that and do it in a relatively quick way. So you kind of describe what you want, and then, you know, either with or without an NDA, and then we go from there and we figure out whether it's possible or not.
I'll just add to that answer. The potential user shouldn't have to think about whether you fit into our model. It's our job to figure out if we can make your prototyping work.
Yeah, absolutely. So I mean, you know, any idea that you have, if it's semiconductor related, we can work with you to kind of help you figure out if it works. If it's not semiconductor related, we probably won't have the skills to help you with.
Okay, no problem. Thank you for that, and probably will reach out with some project ideas.
Yeah, absolutely.
There are questions in the chat.
One question is, historically, MOSIS was close to 100% defense related. What's the breakdown today in terms of commercial versus defense, and about how many projects run through MOSIS each year? So what I can say is that currently we have a mix of, if we look at all the customers that we have right now that are either in queue or being have already been served recently. I would say that I don't have the actual numbers. I'm literally making this up by thinking about the kind of the customer list and where they are. I would say that we have maybe 50% of the customers are still defense related. And then maybe 25% of the customers are just commercial. And so defense related includes commercial defense related projects. And then maybe 25% of the customers right now that we have lined up are academic. In this last year, especially since we've started to kind of aggressively grow Mosis 2.0, we're probably looking at working with it this year. If what we're seeing kind of continues, which we expect it to continue and maybe even grow, we'll probably work with 40-ish customers, I would say, this year, and then hopefully next year we'll be in the hundreds as we kind of reboot Mosis. I think that's probably where we'll end up. There was definitely a major downturn, towards the last few years of Mosis 1.0, but we're definitely seeing a lot of interest, and our engineering managers basically are talking to people, at least 5 to 6 customers, I should say. So that's and probably actually more than that. So that's kind of what we're seeing. We're also working on, I should add one more thing. We're also kind of working on a program where we work with people who are submitting projects, submitting grants, and providing them with letters of support and anything they need to help them make their grant successful, with the idea that then they can come back and work with us, downstream. So Jim Murray had a question, but Gene Dansker told everyone that he was playing Atari in 1981, so I thought I'd just read that out before answering the question. Jim Murray said, Mosis 2.0 addresses issues important at the national scale. How does it reach out to other geographical regions? So I would say that there's a couple ways that we do that. The most natural way right now is because we are, within California Dreams, we're working with other hubs. And I mentioned a few of them, so both Swap Hub and Midwest Microelectronics Consortium. And it's not that those are the hubs that we're working with, because those are the only hubs that we are going to work with, period. It's just that we're doing a lot of stuff within our own hub, and then we're also slowly trying to expand in a way that as we expand, we're successful with those interactions. And so, we hope to eventually expand and work with all 8 hubs. So that is the most natural geographic expansion. I mean, the other thing is, of course, that, the facilities that we're giving people access to, especially the commercial ones, are all over the place. And then there's also other facilities that are interested in working with us that we're talking to that are not associated with California Dreams, but are US-based facilities that maybe need a layer of engineering support between them and customers. And so there's a number of different ways that we're doing that. I would say that our approach right now is to kind of identify what we can do, and then make sure that we are, whatever we choose to actually do to expand our footprint and our capabilities, we do it in a way that's consistent with our capabilities, and to make sure that when we bring something on board, we can then offer it to customers to actually do their research and prototyping and do it successfully. Zach said, really nice talk, Rehan. Thank you, Zach. I appreciate it. How do you see the interest of students to engage with Mosis 2? This was a big part of the original Mosis. I think this is very important. Like, as I mentioned in my when I was giving the introduction, one of my buddies at at Berkeley said something like, "Oh, I taped out, my first 2 tape outs with Moses," and that was a very important part of what Moses did. And that's something that, as a faculty member, it's very important to me. I think that there's a couple of ways that we want to reach out and engage with students. So one way is actually something I already mentioned, is this approach where we work with faculty members who are writing grants, and we actually help them on the front end so that we can kind of give the people who are reviewing their grants confidence that whatever they propose will come through, and via letters of support, as well as even contributing whatever knowledge that we have to helping them frame the grant. And so that's something that we're doing, which then naturally leads to student interactions. There's also workforce development efforts, and so we have fairly significant workforce development efforts already going on in the nanofab side. We are also this summer kicking off an analog measurement workforce development effort, so we can have people really trained in measuring analog circuits. And then I think the plan would be to expand these to also include circuit design type efforts. And that is not necessarily run through Moses, but where Moses works with people who are running tape out classes, and so there's discussions associated with that as well. I think those are the ways that we are actively engaging with students, and those, like you said, it's a critical part of what we do. Enabling rapid prototyping is only good if you have people with ideas, and in order to have people with ideas, you have to have the next generation of the workforce. So I think that's definitely a key part. There's definitely other things that we could do as well, but I think that given our overall resources, what we're doing right now is kind of hopefully we'll make some of these successful and then move on and start implementing other approaches as well.
I think all the questions are covered, right, Rehan? Do you think you have any in the queue?
No, although somebody did mention to me privately that they used it in 1982 in Stanford, Moses. So that's great to hear.
Yep. And you got some great talks and an A+ from Zach, so that's a success.
Amazing.
Okay, well, we're over time. We had up on the screen the QR code for the page for the seminar series, so please follow that and go to our YouTube channel for previous talks, and this talk will be up soon. And click like and subscribe so that you can see all the seminars that we miss. And then I seem to be 2 minutes behind Amy on her slides here, but there was a list of upcoming seminars, with more good talks to come.
I didn't realize that we have an Instagram page, actually.
We have it all. So please go subscribe on all the platforms on which you live. There is one more question, and I'm sorry we're over time, but I didn't see there's a Q&A window here. I'm gonna try to read that one. Will the program support workforce development, especially related to technicians or tool maintenance? That answer may have 2 parts.
Yes, I think the answer is yes for the technicians. I mean, we are literally doing that on a regular basis for the clean rooms. There's also the possibility of doing that for ours on the circuit side. I mean, we already are implementing the analog measurement class that's going on this summer. So I think that the answer is absolutely yes, and we're already doing it to some extent. Yeah, I think that's how I would put it.
And then, of course, students involved in funded research projects or otherwise have opportunities to tape out at Moses, for example, through the upcoming GAN Prototype Accelerator and others. So I think, Rehan, unless you have anything else to add, I think we can wrap up. And thank you once again for being such a great speaker and your leadership of the Mosis 2.0 organization.
Well, thank you for getting California Dreams here. So none of this would have been possible without that. And thanks everyone for coming and listening, and the questions. Hopefully we can interact more and continue to grow this effort and accelerate prototyping for the US, because it is such an important thing and it's never been more important.
Yep.
If 80 more important, the 2020s are far more important than that.
And one more reminder, if you liked Rehan's talk today and want to hear more about his own research agenda, come back on July 11th.
I will talk about some parts of my research then as well, yes. All right.
Okay.
Thank you, everyone.
Thanks, everybody. Bye.